Vertical dynamics are basically anything that is moving up or down, okay? And so if it's moving up or down, it has at least two forces acting on it. Well, actually, that's not true. If it's moving down, then it could just be gravity. But if something's moving up, it definitely has two forces working on them. So, what are those two forces? Obviously, the downward force of gravity. But if it's moving upwards, then there's got to be an upward applied force. If it's moving downwards but at an acceleration less than 9.81, then there also has to be an upward applied force. So think about elevators. If you're on an elevator, you move down, but you don't move down at an acceleration negative 9.81. That would be incredibly dangerous, and that's why falling elevators are really, really bad things when they're up in tall buildings. So, of course, even though the elevator is lowering you, there's still an upward force happening because, of course, you don't want to fall at that acceleration due to gravity. That's just way, way too fast. So those are your two forces anytime you have vertical dynamics. So we can think of this in two ways. We can look at the elevator as a whole, right, where you have a force of tension going upwards, and then there's a force of the elevator going downwards, okay? So that is just externally, that's what's going on there. If we just look at, say there's a person in an elevator on a scale, then there's a whole other system kind of going on here. Oh, and there's the force of the person in the elevator too. But say there's a person on a scale in the elevator. I want to know what's going to happen, because we now know that our weight is really, our weight is really just our mass times our acceleration. So in an elevator, that might actually change a little bit, because if we also have an upwards force that's forcing us up or letting us go down, but not at the same acceleration, how's that going to affect it? Okay? So really, we're not looking at the whole thing. I want to look at just this system where this guy is standing on this scale right here. And of course, there's the force of him on the scale and the force of the scale on him, right? The normal force. So I want to know what's going on there and what's going to happen, because guess what? If you step in an elevator, you step on a scale and you make the elevator go up, your mass is going to change. Really, your mass isn't changing, but the scale reading is. And that's because your weight is changing. If you go down, your weight's also going to change. You're going to see a change on the scale. So what exactly is going to change? How is it going to change? So try to think about that. So basically, I want to know, if you're on an elevator and you're standing on a scale, what is your apparent weight? Not your actual weight, because we know that your actual weight will just be mass times gravitational acceleration. But what's the apparent weight? What is the scale reading for you? Okay, so this is what you usually look like when you're standing still, this first one, right? Our normal force and our gravitational force are equal and opposite. So that's nothing new. That's something we've seen a bunch of times now, right? And we know that force of gravity is equal to mg. So what's this next one looking at? So we have a normal force that's larger than our gravitational force, okay? So I want to know, what's happening with the elevator at this point. Well, think about the fact that whichever direction the greater force is the direction of the acceleration. So this is telling me something where the elevator is going up because my acceleration is going upwards, okay? So I know that. But what I want to know is the scale going to read something, a larger number or a smaller number? So think about the fact that you're going up. Remember, try to feel that feeling when you're going up in an elevator. What does it feel like? It feels like you're being pushed down. The reason is because the normal force has to work harder to keep you upright, okay? So this is actually where the scale will read something larger. So your apparent weight is always the Fn value. So if you're accelerating upwards in an elevator, that means your normal force is larger than your gravitational force. So that's your direction of acceleration. And so therefore your apparent weight is larger. Okay? So apparent weight larger here. And again, that's because Fn is larger. So apparent weight is always your normal force, okay? Because it's basically how much force does the ground now need to exert to keep you upright. And when you're accelerating upwards, it needs to exert more force, okay? So then this last one, obviously the elevator's going down because our gravitational force is larger than our normal force. And so that's the bigger one. So that's telling us my acceleration is downward. So the elevator is going down. But try to remember that sensation when you're on an elevator and you go down. What does it feel like? It almost feels like your stomach kind of lifts up. Everything lifts up a little bit. Remember that feeling when an elevator goes down? That's because it kind of is. Your normal force that was used to counteracting gravity all of a sudden doesn't have to counteract gravity as much, and it takes your body a second to adjust to that. Okay? So you're actually feeling lighter when you do that, and since your normal force doesn't have to do as much work, then your apparent weight is going to be smaller. So what that means is if you are on a scale on an elevator and you need to gain or lose some weight, well, it's going to be really easy. So say you need to gain some weight, you got to get those gains. So then you're going to just like go in an elevator and press a floor that's above you and your weight's going to go up. And then if you get on an elevator and you want to lose some weight, well, then you're going to go downwards. You're going to stop at a top floor. You're going to go in the elevator. You're going to get on the scale, and then you're going to go downwards. And you're going to see that weight go down. Isn't that exciting? Okay, so that's that. That's how that works, but I know it's kind of difficult. Okay, so we're actually going to solve a few questions involving these vertical dynamics and these elevator questions. So really just pay attention to the direction of the acceleration. That's going to tell you a lot, okay? So persons on a scale in an elevator, told you we're going to do these, accelerates downward at 2 meters per second squared. Okay, so what is that? If they're accelerating downwards, then my downwards force should be greater. So we're dealing with this scenario right here, this third one, okay? So their mass is 60 kilograms, so I want to know their actual weight and their apparent weight. So let's start with a free body diagram, as we always do. If they are accelerating downwards, remember that means their downwards force should be greater than their upwards force. Of course, the downward force is force of gravity, and the upwards force here is normal force as they are standing on a surface. So actual weight, that's just how much does normal gravity push you down to the earth. Okay, so that's just mass times gravitational acceleration. That's all that is. So that's all we have to do. It's their mass was 60 kilograms, and of course gravitational acceleration is 9.81 meters per second squared. So that gives us an actual weight of 5.9 times 10 to the 2 newtons. We do need 2 significant digits here, so I just rounded it right to 2 significant digits. Okay, there we go. So that's their actual weight. So if they are moving down in the elevator, is their apparent weight going to be larger or smaller than the 5.9 times 10 to the 2? Well, let's find out. So we're going to do this the same as usual. Always make your positive direction the direction of the acceleration. Acceleration is downwards, so I'm going to make downwards positive. Okay, And then I need to use Newton's second law. We're still doing that. Anytime we draw a free body diagram, we always know we're using Newton's second law, and that is that the sum of forces is equal to mass times acceleration. The sum of the forces here, well, my Fg is the positive one, so I'm going to write that one first, and then I'm going to subtract my normal force, of course, because, well, yeah, that's the one that's in the negative direction here. Okay, and then I want to find apparent weight. So remember, apparent weight is the normal force. So I'm going to rearrange this to solve for the normal force, and I get the fact that Fg we should subtract ma from that. Okay, and that's how we get normal force. So we found our force of gravity, so that was the 5.9 times 10 to the 2 newtons. And from there, I'm going to subtract mass times acceleration. So the mass is 60 kilograms, and the acceleration is 2.0 meters per second squared. Remember not to put the negative in for that, or the well, I guess it's already positive. But remember, in this first statement, you always account for negatives and positives, so nothing after this should have to be negative or positive, okay? You've already accounted for all that. Okay, so my normal force is 4.7 times 10 to the negative 2. So that actually makes sense because my normal force should be smaller than my gravitational force at this point since it is accelerating downwards. So that means that your apparent weight is much less and the scale will read less for you. So how nice is that? Okay, so let's do another example. Here we have a person and an elevator have a combined mass of 6 times 10 to the 2 kilograms. Okay, so it's combined. The elevator cable exerts a force of 6 times 10 to the 3. Okay, so what this is telling me is that we care about the elevator, the cable, and so we're not actually looking at a person on a elevator anymore. We're looking at a whole elevator. So we're actually going outwards and looking at that bigger thing. So that's really important to us. So actually when I draw this free body diagram, this box represents an elevator, whereas the one before it represented a person. Get it, right? Yeah? Totally clear? Okay, so I definitely have force of gravity moving downwards. And then the force of tension is upwards, but here's the problem. I don't actually know which one's bigger. So I'm going to go ahead and just, I would usually not even do this on paper, but I would quickly kind of take my calculator and say, okay, how much is the force of gravity? Because that's just mass times gravitational acceleration. So 6 times 10 to the 2 is just 600, and you multiply that by 9.81, and you get 5,886, which another way of saying that is 5.9 times 10 to the 3, which is not what I'm going to use. The reason I did that is just so I can compare it with the 6.5 times 10 to the 3. So I know which one's larger. It looks like that force is larger, so it's going to go upwards. So we're going to make the force of tension a bit bigger. Okay? So that's kind of what I'd usually do in this situation where like, I don't know which acceleration is larger. Then I'm going to go ahead and just check. Okay? So there we go. So there's my force of tension. And I know here now that since force of tension is bigger, I'm going to make upwards positive because that's the direction of my acceleration. Okay. And then this is just kind of like a regular Newton's second law question. Since it gave you elevator, it's just trying to trick you to think that it's the more complicated one with apparent mass or apparent weight. But it's not at all. So there you go. So sum of forces. Well, force of tension is positive, so I'll start with that, and force of gravity is negative, so I'll subtract that. Should equal to mass times acceleration. And of course, we are looking for the acceleration, so we are just going to rearrange this guy for acceleration just by dividing both sides by mass. I'm going to turn force of gravity into mg and then divide by mass. Okay, let's do that. So force of tension was 6.50 times 10 to the 3 newtons. And 6.00 times 10 to the 2 kilograms times g is 9.81 meters per second squared. Divide that by the mass. And what do I get for my acceleration? I get 1.02 meters per second squared. So yeah, and that's to be expected because honestly, as we saw, the force of tension wasn't that much bigger than the force of gravity. So yeah, it's accelerating upwards at a nice pace, nice slower pace. Okay, I'm going to do one more example with you here, just to, again, get those vertical dynamics. What's happening? I want to show you that there's more than just normal force that can be pointing upwards. So we have a skydiver practicing jumping out of an airplane. During the jump, the parachute is unopened, and the air resistance, finally we get to deal with a little bit of air resistance, acting on the skydiver is 250 newtons. So the acceleration of the skydiver during this time is 5.96 meters per second squared down. So we want to calculate the mass of this skydiver. Okay, well, let's, again, I just gave you a lot of information, but let's just start with our free body diagram, then go to Newton's second law, and honestly, things start to work themselves out. So what's happening to this skydiver that, surprise, surprise, is shaped like a box? Of course, gravity going downwards. But there is a force going upwards, but is it the normal force? People just really like to do normal force upwards, but the thing is, that only works if it's on a surface. This is not on a surface. So, what is going upwards? Well, it's air resistance is giving it a force upwards, right? Air resistance is a form of friction, so I'm going to call that force of friction. And there we go. That's actually the force that is going upwards. Okay? So acceleration of the skydiver is downward, so I'm going to make that positive, and then I'm going to go to Newton's second law. Net force is equal to mass times acceleration. What is my net force? That's force of gravity minus the force of friction due to air resistance, and that should equal to mass times acceleration. So again, we're looking for mass. Another problem here, we kind of ran into this last lesson where there's mass is part of Fg, and it's part of this guy over here. Do you remember how to solve for mass? Okay, well, what I'm going to do is I'm going to get everything with mass to one side of the equal sign. I'm going to get everything with friction to the other side. So kind of at the same time here, I'm going to subtract MA from both sides. And then I'm going to add force of friction to both sides because I can do this at the same time because, well, that's just what we can do because now we're math wizards because you're in physics. So what do you get here? That means you get mg minus ma is equal to the force of friction. What do? Do you remember? You substitute out an m, so then you get just g minus a in the brackets, and that's equal to the force of friction. And now I can divide both sides by g minus a. Okay, so that's what I'm going to do. And I get mass equaling the force of friction divided by g minus a. Okay, let's find the mass of this skydiver. Force of friction, again, that was due to air resistance. That was 250 newtons. G is 9.81 meters per second squared. And my acceleration, 5.96 meters per second squared. Yay, we got it. Okay, well, we don't quite got it, but we basically got it, right? So what you should get there, make sure you put your denominator in brackets when you plug that into your calculator. So it should be 250 divided by bracket 9.81 minus 5.96, close the bracket, and you should get 64.9 kilograms. Okay, I was given 3 significant digits in the question, so of course my answer should be 3 significant digits. And there we go. Okay, so that's all vertical dynamics I have for you today. Definitely this is probably the most difficult one people have a hard time getting. And then what I want to get through to you with these other 2 examples is that this guy going against gravity is not always normal force. You only ever use normal force when it's sitting on a surface or standing on a surface. Okay?